of you watching on the video. I'm David, and I'm the coordinator of the Maths Learning Centre. And now you know what I look like. I can turn the video off. All right. So it's semester 1, 2017, and this is the revision seminar for Maths 1M, and I'm going to talk about trigonometry. So the purpose of these revision seminars is to talk through particular topics in particular courses with the hope to giving you some skills that you might be able to use when you're doing these things on your own, to organise these things and maybe in a different order. Might make more sense. And yeah, try and connect the ideas together. So as far as I can tell in the trigonometry bit of your course, you define the trig functions using the unit circle, and there's a few things about trig identities, and there's some things about trigonometric graphs as well. And so I was just going to talk about those things. Please do interrupt me at any point and ask any questions you might have, even if you think I'm about to say it anyway, and I'll just tell you if I'm about to say it. And yes, I'd prefer you ask me questions because this is for you guys, and the more questions you ask, the better chance of getting the thing that you want, and the better chance of you guys listening getting something that you didn't know you wanted because someone else asked about them. Oh, the back row of this lecture theatre is a different colour. I've never noticed that before. Sorry. It's the end of the semester. I'm struggling a bit. Okay, so trigonometry. The literal meaning of the word trigonometry is the measurement of triangles, and that's how it started, and then it became something else later in its life. And so I'm not going to necessarily start with the triangles in the same way that you would see it elsewhere. I'm going to start with what matches most closely with what happens in your course. So the idea is that different right-angled triangles have particular relationships between their sides. And the relationships between the sides of triangles and the angles of triangles is essentially what causes a triangle to have a certain shape. And so it's about the shapes of triangles. And the classic definition of the trigonometric functions is this. If you have a right-angled triangle with an angle just here, and if this length is 1, then this length is cosine of theta, and this length is sine of theta. And we write them like that as functions. So sine isn't a number, it's not something that's multiplied by theta, it's a list somewhere that every theta has an answer for sine theta. So it's sine of theta, technically. And it's actually even shortened. The full name is SINE, and we've shortened it to SIN. In other languages, they shorten them differently because they call them whatever they're called in their own languages. So here we have sine and cosine, which we pronounce as sine and cos. And so, yeah, and what that does is it allows us to figure out the sizes of any other right-angled triangle. So if we had one of length, where this length was 5, well then the triangle would be 5 times bigger, and this would be 5 cos theta, and this would be 5 sine theta. And if we had one that had length of 0.5 here, then this would be 0.5 cos theta and 0.5 sine theta. That's one of the ideas. And if you had an angle, a triangle where it wasn't already 1, you could divide everything by whatever was in this spot, and that would tell you what the sine theta and the cos theta was. All right, so the other one that is very common is this one, where you put the 1 on this side. And if you put the 1 on that side, then this is tan theta. And the tan theta is essentially telling you about the slope of this line here. as it goes across 1, it goes up tan theta, which is exactly what slope is. It's how far it goes up or down for every 1 across. Okay, and in case you are interested, this side is sec theta, just in case you wanted to know. Not that it's important, but you might want to know. And mathematicians get a bit lazy and forget to put the brackets in next to these things. Okay, so that was the original definition. And the problem was that there are triangles more than right-angled triangles, and there are triangles with angles that are bigger than these angles here can be, and so we had to define what cos and sine were for angles that were bigger than the sizes of angles that fit inside a right-angled triangle. And so what we did is we redefined sine and cos to be about a circle. And that was the reason is because this length of 1, as it moves back and forth along here, traces out a circle, and so we just traced out a full circle. And so we did this. We made a circle of radius 1 centered at the origin of a coordinate plane. Oops, I may just move that. Unlike Michelangelo, I am not able to draw a perfect circle. And what we did is we said that given a specific angle, we can draw our little triangle in there. And then that means that this height here is the same as the y-coordinate of this point. And this length here is the same as the x-coordinate of this point. And so we redefined sine theta and cosine theta to be the x-coordinate and the y-coordinate of a point on the unit circle. And then, because of, well, many reasons, we redefined how we measured angle too. So instead of angle being this nebulous idea of the size of the space between two lines, we've redefined angle to be a literal distance measured around the edge of this circle. And so the angle itself became this distance here. So we found a new way to measure angle, and that's measuring an angle in radians. And that's a really nice way of measuring angle, because, like, what even is an angle anyway? Seriously. You know, when you look at, talk about an angle between two lines, is it the area? Is it a distance across the end? Like, what is it? And so we've just carefully defined it as a literal distance around the edge of a circle. And so we've redefined everything. And so we can now figure out, based on this circle, what sine and cosine are for every possible angle of any possible size in any possible direction. We can go this way as far as we like, and we can go this way as far as we like, and calculate an x and a y coordinate. All right, there you go. Nice. So that's the story. I should tell you where tan is in this picture, just so that you know. So tan, as I said earlier, is the slope of this line. But it's also the height of a triangle whose bottom is length 1 with the correct angle. So if you measured an angle here, then this is length 1, and you can make a triangle of height, whatever height it needs to be. So you can actually draw a tangent to your circle at the very edge here where you start measuring angles, and this distance here, that is tan theta. And that's why it's called tan theta, because tan is short for tangent. It's a distance along the tangent. That's why it's called tan theta. So it's this height here, and if the point causes you to draw to meet the tangent down the bottom here, then that will give you a negative value for your tangent. Okay. So, I'm going to stop here and allow you to ask me some questions about this bit of the trig. If anyone has any things they would specifically like me to say before I launch into other things. So what sorts of things would you like me to talk about in this bit? Things that you try to do that you're not sure how to do, or you feel you're pretty sure but you keep getting them wrong, or things that you've noticed and you want to be sure that they're really true, anything like that. Sorry? Exact values. Cool. Excellent. That's a good one. So exact values for specific angles, is that the sort of thing you mean? Oh, so any given angle including the ones that are like over here? Okay, cool. That's good. Okay, so I suppose I should at least mention that angles measured in radians tend to come in multiples of pi. So a circle has a circumference that's pi times its diameter, which means that this half of the circle is pi long. It also means that in this direction, that's pi long as well. But we tend to call that minus pi because it's going in the opposite direction. Because we call anti-clockwise the correct direction as a mathematician. The reason we do that is it covers the angles that we're interested in for triangles first. If we go anti-clockwise here and we define sine and cos as the x and y coordinates, then it will neatly define sine and cos to be positive when you have angles that fit inside right-angled triangles, and it will define cosine to be negative when you have angles greater than 180 degrees, which is necessary to make the cosine law work. So that's why. And what that means is that when you see an angle like a third or a half of pi, you can, and this is how I think about it, I think about it as breaking up this piece here into pieces. And I know that as in degrees, this straight angle is 180 degrees. And so I know that 180 degrees goes with pi radians, and everything I do is based on that calculation. But to be honest, pretty much all of your trigonometry in Maths 1M is done without degrees at all. It's all in radians. So as long as you can have an idea of how big an angle is by comparing it to pi, you should be okay. All right. So there are three classic angles which have fairly nice answers for their sine and cos, and they are pi on 4, pi on 3, and pi on 6. Which, if you're in degrees, pi is 180, and so we want a quarter of 180, which is 45 degrees. Pi is 180, and we want a third of 180, which is 60 degrees. And pi is 180 degrees, and we want a sixth of 180, so a sixth of 18 is 3, so 30 degrees. And once you're doing this for a while, you'll just get used to those and be able to match them up, but you can always compare them to the size of 180 degrees to see if you want to figure out how big they are. And these are your classic angles. And these are the angles that always used to be in set square in the set squares for people who did engineering and architecture. And so they were pretty cool angles to use. And the nice thing about these angles is that these angles fit inside the sorts of triangles that are easy to construct. So I can construct two triangles based on familiar shapes from which I can calculate the sine and cos of these, and that's how I think about them. So if I have a square like that, and I cut it in half, then that's 45 degrees there, which is pi on 4. And my square, traditionally to do sine and cos, you would put a 1 in this position, but I'm going to do this. My square has edges of 1. I'm going to do the shortest edge I can find and call it 1. And according to Pythagoras' theorem, this edge should be the square root of 1 squared plus 1 squared, so it's root 2. So I think about this nice little triangle just here, which is half of a square. And I think about my angle of pi on 4. And then I can do sine and cosine. So I know that if this edge was 1, excuse me, so there's two ways of doing it. One is to know that, is to do this, and divide everything by the root 2. In which case, we know that when this is 1, that's sine theta over here. And that's cos theta down here. And when this is 1, that's tan theta there. So that's one way of thinking about it. The other way is to know that, well, eventually you're going to have to divide by this. So you can just go 1 divided by root 2. And this one divided by root 2. And the other thing that you can do is go, well, I know that the tan is going to be the slope of this line, so it will be the rise over the run, which is 1. So there you go. That's ways of remembering it. I didn't usually do it that slow when I was in my exam. In my exam, I would draw, the first moment I could draw, I would draw on my scrap paper that triangle. And the second thing I would draw would be this. This is an equilateral triangle. All of the edges are supposed to be the same. And in an equilateral triangle, all the angles are the same too, and so they're all 60 degrees. And so I'm going to cut this one in half as well. And in this triangle, I'm going to choose the shortest angle that I can possibly choose. Not shortest angle, the shortest length I can possibly choose, and that's going to be here, 1 there. And if that's 1, that has to be 2 because we cut it in half. It's an equilateral triangle, so that's 2. And this one, because of Pythagoras' theorem, will be root 3. And it was much easier. I didn't even have to do Pythagoras eventually. I could just draw my triangle and go 1, 2, root 3. And I got used to it. So this angle over here is pi on 3. And this angle over here is pi on 6. Because I know I can fit 3 triangles in a straight angle, so this one's pi on 3. So I get that sine of pi on 3. Crap, sorry guys. I can create this triangle by dividing everything by 2. And now this becomes sine of pi on 3, and this is cos of pi on 3, and this is tan of pi on 3. And the cos and sine and tan of pi on 6 are done from the other corner. So there you go. So I get cos of pi on 3 is 1 on root 3. Sine of pi on 3 is, no, damn it, 1 on 2. Drawing the wrong thing. 1 on 2, root 3 on 2, and tan of pi on 3 is root 3 on 1. And then cos of pi on 6, which is up in this corner. I should draw a little triangle just a second. That's this corner. And this one is this corner. Cos of pi on 6 is that. Sine of pi on 6. Damn it. is that. Cos is the one next to it. And tan of pi on 6 is 1 root 3. Okay. I may have done a botched job of that, I'm sorry. But that's what I would remember. And in fact, this is pretty much what I would draw on my scribble paper. These two triangles and a unit circle. Because the other thing I can always do from my unit circle is calculate what the angle is for the ones that are on the axes at least. So on my unit circle, I know that pi on 2 is halfway across the top. So that point there has coordinates 0, 1. And so I know that cos of pi on 2 is the x-coordinate. Sine of pi on 2 is the y-coordinate. Tan of pi on 2. Well, if I was drawing a tangent here, that doesn't meet the tangent. So there is no, it doesn't exist. If I drew a point here, it would meet the tangent, and as it gets closer, it gets higher and higher where it meets that tangent until it's directly vertical, they're parallel, it's not going to meet it at all. The other way of doing it is know that it's sine divided by cos, which I hadn't gotten up to yet. And plus, the slope of that line is perfectly vertical. There is no slope. So multiple ways of dealing with the whole thing. And this is where we can start to see what might happen if I extend beyond the, that first corner, officially called the first quadrant. When I get over in this corner, if I get all the way down here, then I know that cos of pi, this point over here is minus 1, 0. So cos is the x-coordinate, sine of pi is the y-coordinate, and tan of pi is the slope of that line, which is 0. It's a flat relative to the page line. So I can, from any angle that's at least producing something that's on the axes, I can create just from the coordinates of those points exactly what the sine and cosine of and tan of those points are. Beautiful. However, that leaves all the spaces in here. Now, technically, if I had like pi on 8, I wouldn't know exactly what it was from the information that I have here. But I can at least do it for things that are related to this pi on 4 and pi on 3 and pi on 6. So, works best with an example. Is that what I want? Yes. Find sine of 17 pi on 6. So I can imagine 17 pi on 6. All right, well, let's see. That's pi on 6, which is a third, no, which is a sixth of pi. So I divide that pi into 6 pieces, like that. And 17 pi on 6 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. There. 17 pi on 6 goes all the way around once and ends up in this spot just here. That's where it ends up. And I literally counted 17 pi on 6. Now, other people might do something different to that. They might calculate what this is as a mixed number. They might calculate that 17 sixths is the same as, well, let's see, 12 would be 2 and then be 5 left over. 2 and 5 sixths. That's one way of doing it. And so if I've got 17 sixths of pi, that's 2 pi, which is all the way around, and another 5 pi on 6. So that's another way of doing it. So my first thing I've noticed is that this angle, even though it's a longer angle, the sine will be the same as what it would have been for 5 pi on 6. So far I've gotten this. It's a 17, by the way, not another pi. Okay. And most of the time in my head, I might read it aloud as 5 pi on 6, but in my head I'm seeing it as 5 sixths of pi. So the next question I need to ask myself is, what is the y-coordinate of that point? Because that's what sine is. Sine is the height of this above here. Well, it lines up exactly with this one over here. It has the same y-coordinate as sine, as the point produced by pi on 6. And so I can say it's the same as sine of pi on 6. And I know what sine of pi on 6 is. My little diagram tells me that it's, pi on 6 is there. Sine of pi on 6 is a half, because it's this opposite edge when that length is 1. Classic. That's how I would normally do it. I would literally try and measure across and compare it to what's over here. But sometimes you can do it a little bit different. Let me do cos of 7. Sorry, that drawing is not very clear, is it? I don't know if I can fix that. Is that any better? Not really. It's fuzzy, isn't it? Yeah. Okay. I'm going to do cos so that we can have a different way of doing the same thing. Okay. So I know it produces the same point. It's still just there. Actually, I'm going to need a bigger diagram than that. Okay. What I can do is I can compare what's in this triangle to the angle I really want. So I know that this distance, it was 5 pi on 6 this way. So the angle between here and the x-axis is pi on 6. That's one way I can do it. I can figure out the angle between where I am and the x-axis. And that means that this triangle here, this literal length must be cos of pi on 6. Because this triangle just here has 1, it always has 1 if it's in the unit circle, and the angle is pi on 6. And so the height must be sine of pi on 6, and this must be cos of pi on 6. So let's see. Because of the triangle I've just made, I know that cos of 17 pi on 6 is the same as cos of pi on 6, except this distance is pointing in the negative direction. Cos is this distance, but it's literally where it lines up with on the x-axis, and it's on the negative side of the x-axis. X-axis, x is positive on this side and negative on this side, so it's minus cos of pi on 6. So because this point is over here where x is negative, the cos will be negative. So what I can do is I can say in my head, I'm going to figure out how far my point is from the x-axis, and then I'm going to say, well, it must be the same as cos or sine or whatever I'm trying to calculate of that angle, and then I can decide whether it's going to be plus or minus depending on which side it's on. I'll do one more of them in a second. Cos of pi on 6 came out to root 3 on 2. There's a minus there. All right. So be brave and ask questions if you have any about this. All right. Cool. So I'm going to draw some pictures that go with my thinking about this. So tan cos is positive over here, because that's where the x-axis has positive numbers, and that's where cos is going to be positive when the x-axis has positive numbers. And sine is positive up here, because that's where the y-axis has positive numbers, and sine is the numbers on the y-axis. And tan is positive here, because that's where the slope of the line is positive. If I draw a line here or a line here, we get a positive slope line. Some people remember that with a little acronym that says that they're all positive here and sine is positive here and only tan is positive here and only cos is positive here. I find that really difficult to process. I prefer to have this picture that just tells me where they're positive. So when I was looking at this one above, I went, okay, cos is going to be the same as what it is for the angle that gets to the x-axis, and because it's on this side, it must be negative. Yeah. All right. How long have we been doing this for? All right. So, that's figuring out all those angles. So now for any angle, well, for any angle that's a nice number, I can figure out an exact value for the sine and cos by lining it up with how far away from the x-axis it is, and then deciding whether it's plus or minus. I have a question that I want to ask you to just see how you're going with that. Could some people please tell me some angles in radians that produce minus 1 on root 2? What goes in this spot, do you think? Sorry? Minus pi on 4. So, just a second. What else have we got? I'm going to brave and pick a crazy one. I'm not going to be that crazy. Yeah, well, let's check them all, hey? And see which ones actually work. We can test them. Okay, so minus pi on 4 is here. And the angle that gets me back to the x-axis is totally pi on 4. So cos of minus pi on 4 will be the same as cos of pi on 4, except cos is positive over this side, and so it's not this one. So not that one. 3 pi on 4, let's see, 1, 2, 3 pi on 4 is there. And that's on the negative side. And so, yep, it is going to be that. 5 pi on 4, 1, 2, 3, 4, 5 is there, which is on the negative side. 13 pi on 4, that's the one I did. I'm probably wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, yes, that's in the same spot as 5 pi on 4. And 11 pi on 4 would be 2 pi on 4 back from there. Beautiful. Right, good. Okay, I think we can do that. So I could have chosen some negative ones. I could have done minus 3 pi and 4 would have done it as well, and that would have produced the same answer. In fact, minus any of these would have produced the same answer, because cos of plus something is always the same as cos of minus something. Beautiful. I just wanted to check that. So what you've discovered there, I haven't got all the solutions, is that if you're allowed to use any angle you want, there's infinitely many solutions to an equation like this. Right, so there has to be a way of specifying what all of those solutions are. Now, if I'm only allowed to use this angles between here and here, then I'd only get one answer, and it would be 3 pi and 4. If I was allowed to use angles from 0 to pi and from 0 to minus pi, I would have gotten two answers, which would be 3 pi and 4 and minus 3 pi and 4. So the zone that you're looking at will give you multiple different answers. So when I solve, a trig equation like this, I will go through a certain process and I will calculate what angle would give me the correct value, ignoring the plus or minus, and then I will adjust it to make sure it's in the right zone. So just as an example, if I was actually solving this equation, let's do this one instead. So I'm going to solve the equation sine x is equal to the root 3 on 2 for x between minus pi and plus pi. So first I will figure out an angle that does give me sine of x equals root 3 on 2. Okay, let me do it with a minus so I can show you how I do it actually. So let's see, sine, I'm just going to change the letter and ignore the minus and say that means that my alpha would have to be, let me just think, it's not pi on 4 because that would have had a root 2 in it. Sine is root 3 on 2, so it must be pi on 3 is the angle that gives me that, because it's the opposite side. Okay? But my number x gives me negative root 3 on 2. So let me just imagine where that is. So sine is negative down here. That's where sine's negative. And so my angle must be pi on 3 away from the x-axis. So let's see what we get. So therefore my x is actually minus pi on 3 because that's clockwise, and 1, 2 pi on 3. Like that. Because we've got 1, 2, 3 pi on 3. There you go. That minus 2 pi on 3 could have been done like this. I could have gone all the way pi and then come back again. So it could have been pi minus pi on 3. That's how I would normally do it, because that's how I think about it in my head. But it does beg a question. Most other functions that we know, like squaring and square rooting and adding 3 and ln and stuff, they all have inverses that you can undo. And your calculator does, in fact, have a way of doing that. And so it would be kind of cool to be able to go, hey, let's do something to both sides of this equation here, and it will tell me what the answer is. Because that's traditionally how you solve equations, and that's where we get into inverse trig functions. So, here we go. Yep. Go for it.
Can we solve sine by lane using half-angle formula? Because I'm not sure.
Yes, we can.
I'm not sure what's happening.
Okay. I will cover that shortly. Remind me in about a minute when I've talked about this. Okay? Okay. Maybe. Yeah, I will do that. But I just wanted to talk about the inverses while I was at it. So when you're used to seeing equations like this, you're used to doing the same thing on both sides to produce an answer. And the thing you do is the inverse of sine. And so we can define these new functions that are designed specifically to undo the job that sine does. And so we have this thing where we take an angle and it produces a number between 0 and 1, so between -1 and 1. And sine does that. And what we want is a function that goes back this way, that takes a number between -1 and 1 and produces an angle. And that's what sine inverse does. So some people call it sine to the -1. And that's completely different to 1 over sine. What I've done is I've taken the word sine and I've applied the inverse operation to it to create a new word, which I haven't written down. I've just called it sine inverse. And so I'm saying this is the name that does the opposite job. So I've done the inverse directly on the name. Or you could call it arc sine if you wanted. And the reason it's called arc sine is it produces a length of arc. Arc means a piece of a circle. So much so that in French a rainbow is called an arc in the sky. So it's a piece of a circle, and so we're doing the angle part of sine. And in a computer you would call it a sine and not arc sine. So if you were doing MATLAB or MATLAB or even Excel, you'll call it a sine. Okay, but the problem is that we know already that there are a million, infinitely many angles that produce the same answer. And if I have a machine in a calculator, it's only going to be able to produce one answer at a time. And so I have to know which answer it's going to produce. And so when mathematicians thought very carefully about how arc sine and arc cos and arc tan ought to behave, what they did is they said, all right, arc sine and arc cos are only going to be able to produce angles in a certain zone, and you're going to have to figure out, if it's not that answer, you're going to have to figure out what the real answer is, which is exactly what I did here. Arc sine will only produce the answer from root 3 on 2 of pi on 3. But that's not the one I wanted, and so I have to, using my unit circle, figure out the ones I really wanted. Because my calculator or my machine that is arc sine will only tell me one of them. And so the important thing about arc sine and arc tan and arc cos is that they only produce angles here. And I'll show you the angles they produce. Arc sine produces these angles. And arc cos produces these. And arc tan produces these. All right, so the angles that arc sine produces are here, between minus pi on 2 and plus pi on 2. And the angles that arc cos produces are here, between 0 and pi. And the angles that arc tan produces are here, between plus pi on 2 and minus pi on 2. It is very convenient that the angles that arc sine produces happen to be the angles where cos is positive. And the angles that arc cos produces happen to be the angles where sine is positive. That's important, and we'll come back in Maths 1A if you do it. So I warn you now. Arc tan is a whole different choice. But there you go. So it only produces these angles between, this one's between minus pi on 2 and plus pi on 2. This one's between 0 and pi. This one's between minus pi on 2 and plus pi on 2. And note carefully that I have got round brackets here to say that the pi on 2s aren't included, because you can't do tan of pi on 2. And so arc tan can't produce a pi on 2. So when I try to solve an equation with arc whatever, solve tan x is equal to 1 for x between 0 and 2 pi, I could say, well, x won't be equal to, technically, it may or may not be equal to arctan of 1. But what you could think is you could do arctan on both sides, and so you go to x is equal to arctan of 1. And arctan of 1, oh gosh, is pi on 4. And that's a perfectly good angle that's between minus pi on 2 and plus pi on 2, so I can choose that. Only the problem is, x isn't equal to just pi on 4. There's another answer. Okay, tan is positive not just here, but also here. So there's my pi on 4 there, but there's another angle which also produces the same slope. And so tan is positive up here and down there. And if I go to 0 to 2 pi, that means I'm going all the way around here. So I get pi on 4. And also, three pi on 4. No. 1, 2, 3, 4, 5 pi on 4. Okay. So, there is something ever so slightly wrong with what I have written here. X isn't equal to just arctan of 1. And so this line that I've written here is in fact wrong. I need to, if I really want to be absolutely clear and never write anything wrong on my page when I'm doing maths, what I need to do is this. Just tell the person reading it that arctan of 1 is pi on 4, and then tell them what x is. And that will avoid you ever writing anything actually wrong on your page. Some people who mark maths assignments don't care very much about that, and they'll be fine to give you the full marks. Some of them do. And so to avoid it, I would do this. Plus, you know, the mathematics writing includes one of the rules is you should never write anything that is untrue on your page. Okay. So what have we done so far? We've defined the angles. We've been able to attempt to figure out solutions. And we're going to do the trig identities in a second. Just one more thing. What if you didn't have a restriction on the x's and you had to cover all the infinitely many possible answers that it could possibly be? We just said solve cos x is equal to a half without any reference of what x could be. That means x is allowed to be any number whatsoever from minus pi, minus 5 pi, minus 200 pi, up to, you know, infinity at the top. We can take any angle we like, and somehow we have to tell the reader what we're going to do. So I'm going to run through the same procedure. We're going to need to figure out what arc cos of a half is. So it's not pi on 4. Cos is the one next to it. Okay, so it's pi on 3. And so x equals pi on 3 is a perfectly good answer for this. But it's not the only answer. So pi on 3 is here. And what's our cos is positive. That's the one we want. It's a positive a half. So down here would also be another solution of minus pi on 3. Okay. Okay, so far we have that x could be pi on 3, or it could be minus pi on 3. And that's two possible answers so far. But it could also be pi on 3 and another full circle round. So technically 1, 2, 3, 4, 5, 6, 7 pi on 3, or another 2 pi around, or another 2 pi around, or another 2 pi around, or indeed a 2 pi back the other way, so it could have been 1, 2, 3, 4, minus 5 pi on 3. So I could add on to that or subtract from that any multiple of 2 pi and it would still be an answer. And the way that most people deal with that is they go and they pick a number, a letter to represent the missing number which I don't know. And you're not allowed to write a math symbol on the page without telling the person reading it what it means. So you will say for k an integer, and this is one of the fancy ways to write that. For k in the set of integers. The Z comes from the German word for a number, I believe. Because you couldn't use an I, because it would just like have Roman numerals 2. Okay, that's how you would solve such a thing. So some people, when they solve these equations over here, this one like this, they'll actually go straight for the 2 pi k thing and then pick k's that put it into the right zone. I find that a bit confusing, and I usually only do this if there's going to be infinitely many choices. Or like 200 choices, right? If I wanted to do it from like minus 20 pi to plus 20 pi, which I suppose would be only 20 choices, not 200, but whatever. Okay. Beautiful. Now, trig identities. All right. Cool. So, whenever you find anything new in mathematics, one of the important things is to know how it's related to everything else. Mathematics isn't really about how to calculate things, it's about the relationships between things. And so far we've already talked about, how the angles and the triangles and the coordinates on the unit circle are related to each other. But we can get even better than that. We can write down some equations that tell us how things are related to each other. And the first and most fundamental equation, which I probably should have written way earlier, is this. That's the most fundamental one, is that you can figure out tan theta by going sine theta divided by cos theta. Now, if your definition of tan theta is the height that's on that tangent, which is what it was originally back in the day when they first defined it, then this would have been a surprise. Whereas today, they define tan theta to be sine theta divided by cos theta. And then it's a surprise that it belongs on the tangent, which is probably a surprise to many of you. But there you go. That's about the relationship between sine and cos and tan, which means that if you just had a random angle and you happened to know what sine and cos were, you could figure out tan from those two answers. Alternatively, if you had a random angle and you knew what cos and tan were, you could figure out sine from those two answers. Because you could sub them in and rearrange the equation, or rearrange the equation first and then sub them in. This is the one that I find really difficult. I mean, it's not an important one to remember. I just wanted to write it down because it's kind of interesting. That sine theta is tan theta times cos theta. For some reason, that one always surprises me. I look at it and go, really? And then I rearrange it and go, oh, yeah, of course it is. But that's how a lot of these things feel. You look at these formulas and you think, really? That's totally not true. And then not very far away is the original formula. And a lot of the questions where they say, show that this trig identity is true, are about that idea. Trying to rearrange one formula into another. Okay, so that's the sort of most fundamental trig identity. Then there are ones, okay, let's think about this. We're seeing sine and cos and tan as functions now. You stick an angle in and it produces a number out. And most functions that you want, that you're interested in, you're really interested in how they interact with the other things you do to numbers. So you learn that the square root, for example, can be expanded out over division. So if you have square root of 16 over 9, you can do that as square root of 16 divided by square root of 9. And you learn that it doesn't expand out over addition. So every time you learn a new operation that you can do on numbers, it's very important to figure out how it interacts with the other operations that you're familiar with. And so we are going to do it for addition. We're going to say, what happens if you add angles? What does that do to the sine and the cos? And it goes like this. Okay. I may have to go back and fill in some stuff back there. Just leave a gap. What if you had two angles? I'm not going to call them theta and phi because it's difficult to tell them apart by sight. I'm going to call them alpha and beta because it's tradition to use Greek letters for angles. Okay, so it would be really nice if this was just the same as sine alpha plus sine beta, but it's not. That's just not how sine works. It doesn't work like that. In fact, you should know that the only thing that expands out over plus is multiplication by a constant. So if you had like 2 alpha plus beta, you could do 2 alpha plus 2 beta, but nothing else does that. Nothing. So never try and do that with anything except multiplying by a constant. Just good rule of thumb for the rest of your life. If you want to see the proof of that, you can look on my blog. It's very interesting. So sine of alpha plus beta has some other crazy formula which tells you how to figure out what that's equal to. And it's equal to this. There you go. Sine of alpha plus beta does in fact have a plus, but it's way more complicated than you would have liked. It's sine alpha cos beta plus cos alpha sine beta. It does have a sine alpha and a sine beta, but we've had to adjust them by using cos as well. That's just the way it is. I'm not sure if you're expected to remember that in Maths 1M or not, because something you need to ask your lecturer about. I used to remember it I'll get to that in a second. Okay, and if you have a minus, then there's a minus here too. Important that whichever of them has the minus here, then the minus goes with the one that has the sign of that thing. So the beta has a minus, and this is a sine beta, so that's going to have the minus. If they were written around the other way and it was minus alpha plus beta, then you'd have to put the minus on the appropriate bit. Okay, so that's sine. Cosine is similar. It has two pieces. But this time, the coses are together and the sines are together. And this time, when it's a plus here, it's a minus here. It's the opposite of the way that sine works. Sine puts the sines and coses together, and the sines and coses together, and has a plus. Cos puts the coses with each other, it separates the sines and coses. It has the coses together and the sines together, and it has a minus. So they do the opposite of each other, and that's how I used to remember it. I used to remember that one of them put the sines and coses with each other, and the other one separated the sines and coses. What I actually used to remember when I did this is that cos and sine have this sort of one-sided love-hate relationship. So you see sine likes cos, and so it puts the sines and coses together. Whereas cos doesn't like sine, and so it separates the sines and the coses. And even worse, it puts the minus with the sines, because it doesn't like them. So that was my way of remembering it. It's not particularly good, but, you know, there you go. Okay, so this will allow us to calculate a whole lot of sines and coses of exact angles that we couldn't do before. Anything that I can construct out of pi on 2, pi on 3, pi on 4, and pi on 6, by adding and subtracting, I can use this to calculate now. So I might do an example of that in a second. Okay, so we've dealt with addition and subtraction. The other thing you might want to deal with is multiplication. Unfortunately, sine and cos are really not particularly friendly to multiplication. I mean, they weren't very friendly to addition, so it seems reasonable that multiplication would be even worse. Though not always. Sometimes it gets better the further up you go. So they're not that good. The only ones that we have on hand that were sort of really useful on a common basis is multiplication by 2. And the reason we have them is because of these ones. So look at this. Ready? 2 alpha is the same as alpha plus alpha. So if I just replaced all the betas in this with alphas, it would come out to the same answer. Because I've got alpha plus alpha would be sine alpha, cos alpha, sine alpha. And so I get sine alpha, cos alpha, and another sine alpha, cos alpha, so I get 2 of them. There is no beta. So it kind of works. You'd think maybe I can bring the 2 out, which you can't. I mean, you can. You bring the 2 out, but you have to attach a cos to it as well. And cos to alpha is, let's see, we'll have cos alpha, and sine alpha, sine alpha. So they're the double angle formulas. There are such things as called half angle formulas, which are reconstructed from these, but I don't ever remember them because it's not worth my effort. I remember these and I can use them instead. However, there are a few that I have missed. You know how I said to leave space? Well, okay. Right at the beginning, you know how I said sec theta? Well, I need to define how that's related to the other things. So, well, I'm going to need space for 3 things here. Sec theta is 1 on cos theta. Cosec theta. Does your lecturer write that as CSC? Okay. Cosec theta is 1 on sine theta. And cotan theta is 1 on tan theta. You will notice that not one of those has the same reasoning as to what the name of it is. So you're just going to have to know. Like cotan theta is 1 on tan theta, but cosine theta is not 1 on sine theta. And the sec theta goes with the cosine, and the cosec goes with the straight sine, like without the co. So they're not, yeah, they're all different. The sec actually literally stands for secant, which is the length of a line which goes from one edge of a circle to another. And I can't remember where it's this length here, but it also appears elsewhere in the circle too. Okay, cool. But I now remember that sec theta is here. I can get from this triangle to that triangle by dividing by cos theta. Divide that by cos theta, we get 1. Divide that by cos theta, we get tan. Divide that by cos theta, we get sec. So, as you see, what I'm doing is making multiple connections between everything. Because the more connections things have, the better chance you have of pulling them out of your brain later. And But actually, the sensation of understanding in your brain is literally about your brain cells being connected to each other. So the more connections you have, the better you feel that you understand. Okay, there is one trig identity that I have not mentioned, which is the most important trig identity of all trig identities, in so much so that it is called the fundamental trig identity. And it is this. Cos squared plus sine squared is 1. Now, I'm conditioned to write this as an x, but it could be an alpha, it could be a theta. In fact, it could be anything. Cos of 5x squared and sine of 5x squared add up to 1 as well. That is the fundamental trig identity. And it comes all the way back to this definition. It's a right angled triangle. This squared plus this squared equals that squared. And there is one slightly less fundamental trig identity that you can get by dividing this one by cos squared. If I divide this by cos x squared, I get 1. If I divide this by cos x all squared, I'll get sine squared over cos squared, which is sine over cos squared, which is tan squared. And if I divide this one by cos squared, I will get sec. There is another one that you can get by dividing that, but all by sine squared, but hardly anyone ever uses that one. This one's really useful when you come to integrating things later. So, yeah, really cool. So these are like the trig identities. If you have a look in the Maths Learning Centre, or indeed on the Maths Learning Centre's website, you can see a great big list of trig identities which has even more on it than this. So just let me... That's one M, right? There they are. Seriously. And it has, you know, those things I mentioned earlier, the fundamental trig identity and friends, and with some notes for how you can get them from the other things. Oh, these ones I didn't mention, actually. These are called odd and even properties. Cos is an even function, which means that it behaves the way even powers of x work. So x squared, if you do minus x and then square it, the minus will disappear. So cos does the same thing. Cos of minus x is the same as cos of plus x. Whereas sine works the way an odd power of x works. So x cubed, if minus x cubed is the same as minus x cubed. And so sine of minus x is the same as minus sine of x. And tan is odd as well. And then there's the double angle formulas. Now this is interesting. I didn't mention these ones either. These ones just here. And the reason I didn't mention them is because I can never remember them. But I know how to make them. I remember that cos 2x is cos squared minus sine squared, because that's familiar to me. Cos squared plus sine squared is 1, and cos squared minus sine squared is cos 2x. I remember that. But what I can do is I know that cos squared plus sine squared is 1. So if I replace this cos squared with 1 minus sine squared, I'm going to get the bottom one. And if I replace this sine squared with 1 minus cos squared, I'm going to get the other one. And so you'll see I've got some notes for how to create them from each other. Then we have the half angle formulas, and they come from rearranging the cos double angle formulas and subbing in half of x instead of x, and I never use them that way. I'll show you how I use them. Sums and differences of angles, which I did earlier, and then these is about how the unit circle works, and these are just because I had half a page to fill, so I just put all these in because they were fun. So if you shift over cos by pi on 2, you get minus sine, and if you shift it by pi, you get minus cos. And yeah, and they're the derivatives of cos. It's so cool. Anyway, back to the thing. So you were asking, well, how could I use these to figure out, like, pi on 8? Like, so let's see. Oh, and you may be asking, why isn't there a double angle formula for tan? Well, there is, but you can always just do the double angle formula for sine on the top and the double angle formula for cos on the bottom and leave it at that. Okay, so here we go. Let's do an example. I'm going to do pi on 12 because that appeals to me. And I'm just trying to find my sharpener. Okay, so I'm going to do it using the double angle formulas. So let's see. Well, pi on 12 is half of pi on 6. And I know the answers for pi on 6. Oh, exactly with pi of 12. It's pi on 12. Damn it. Sorry, guys. There you go. So pi on 12 is half of pi on 6. It's going to be easier for me to think about it like this. 2 lots of pi on 12 is the same as pi on 6. That's the first observation I'm going to make. And what that means is I can use the double angle formula to calculate the thing I want to calculate. Because I know, well, let's try it and see what happens. Sine of 2 pi on 12, according to the double angle formula, will be 2 lots of sine pi on 12 cos pi on 12. And that doesn't seem helpful because I'm going to need to know what cos pi on 12 is. Like, this is sine of pi on 6, and I know what that is. But this is mixed together a sine and a cos, and I only want one of those. So that doesn't seem very helpful. Let's try the cos. So that's cos of pi on 12 squared minus sine of pi on 12 squared. Okay, well that's hardly better, is it? Because it uses both cos and sine. Again, I only want one of these. I just want this one. I don't want that one. Just a second. I know that cos of anything squared is related to sine of anything squared. I know that, but I know that cos squared plus sine squared is 1. I know that as well. So, let's just be really creative here. I want to figure out what sine of pi on 12 is. So, if I added these together, they'd disappear and I'd have 2 lots of cos pi on 12, which I don't want. I want sine pi on 12. So if I did this minus that, I'd get cos of 2 lots of pi on 12 minus 1. Cos squared minus cos squared is 0. Minus sine squared minus another sine squared. That's looking pretty good. I've got sine pi on 12 equals something. And the something has actually a pi on 6, and I know the answer to that. So let's see. I could rearrange this a bit. If I sort of, well, I guess, I was about to do 2 things at once, but I was afraid of losing my minus sign, so I'm just going to do it in 2 steps. Like that. So I reckon I've got that sine of pi on 12 squared is 1 minus cos. Oh no, there's 2 of these. Damn it. Sorry. When I did minus this minus another one, there should have been 2 of them. Right. much better. All right, well, let's just figure out what this is for a second. Cos of pi on 6 and cos of pi on 6 is half. No, it's root 3 on 2, because cos is the one next to it. Okay? And so I'll divide everything by 2. So 1 divided by 2 is a half. Root 3 on 2 divided by another 2 would be root 3 on 4. And now I have to do the square root. There you go. That's it. It's got a root inside a root, but I can't be bothered trying to do anything about that. They're never really going to get away from that. Get a fourth root of 3 somewhere, but roots don't interact with minus, so I'm just going to leave it. Technically, I should really have checked to see whether it was positive or negative, because when you do a square root, it could be plus or minus. Pi on 12 is over here, which sign is positive there. Okay, cool. So it's the positive square root. If I had been asked for what the exact value of, say, 13 pi on 12 is, then it would have been minus. It would be over here. So that's one way. I could have used, that's using the double angle formula. It takes a bit of work, but I don't have to remember the half angle formulas off the top of my head, so I find it more efficient overall. And I put in a little bit more working than I would normally probably put. Now, I would usually do exactly that amount of working in an exam.
So when you solve it using the identity for subtraction,
Yes?
so we get root 6 minus root 2 over 4.
In just a second, I'm just going to actually show the working for that as well. Or, so you're saying that you have like pi on 12 is pi on 3 minus pi on 4? Does that make sense? 4 pi on 12 minus 3 pi on 12. Yes, okay, good. So that's the other way. You can say, well, 12 is made of a 3 and a 4 multiplied together, which you would get when you added or subtracted things with different denominators. And so you're going to say that sine of pi on 12 is sine of pi on 3 minus pi on 4, which according to the identity should be sine of pi on 3 cos of pi on 4 minus sine of pi on 4 cos of pi on 3. Like that? Good, okay. And sine of pi on, damn it. Sine of pi on 3 is root 3 on 2. That's comforting. Cos of pi on 4 is 1 on root 2. Sine of pi on 4 is also 1 on root 2. Cos of pi on 3 is a half. So you get this. So root 3 minus 1 on 2 root 2. And you're thinking, they don't look very similar. Is that what you're thinking? Well, no, it's a good question. It's not necessary to do this for an exam, but it's a really good thing to do because it makes you better at algebra. So, let's see. Well, if they are equal, if I squared them, I would get the same answer, right? That's what I'm going to guess. Okay, I'm going to square them both and see what I get. So let's see. Half minus root 3 on 4 squared is just a half minus root 3 on 4. Beautiful. And now let's square the other one. So that means I can square the top and square the bottom separately. Okay. So when I square things that are subtracted, I need to go like root 3 squared minus 2 times root 3 times 1 plus 1 squared. That's the top. And the bottom I can square them separately. So 2 squared is 4 and root 2 squared is 2. Nice. So I get root 3 squared is 3 minus 2 root 3 plus 1 over 8. So I get 4 minus 2 root 3 over 8. And if well, they've all got a 2 in them. I can divide the top and the bottom by 2 because I'm allowed to do that with fractions. And so I get 2 minus minus root 3 on 4. That's not too bad. Why don't we put all this over a common denominator? Because that would be 2 on 4 minus root 3 on 4, which is 2 minus root 3 on 4. Yes, they are the same. Because when I square them both, they give me the same answer. Now, that wasn't necessary, but gosh, it was fun. Sorry? This is life. What are you talking about? And if you can't have fun while you're doing your job, then you should do a different job. Okay. Right. So just to tell you, if you are asked to do one of these things in an exam, the people marking it are clever enough to know that there's two answers, and they'll usually have both of them in their solutions, and whichever one you get is the right one. And actually, they're usually dedicated enough to go, that's a different way of solving it that I've never seen before, but it all seems correct. I'm just going to check if it really is the same answer. And so they will check, and so you don't have to worry about it not looking like what the solutions look like. So classic thing that happens when you have exam solutions is they'll only have one of the possible solutions, even if there's more than one, and so it's good to have ways of checking if they're the same. Okay, so, all right, we can do a whole lot of calculations. We've got these trig identities. I should be worth pointing out that these trig identities here, they don't necessarily work in one direction, right? Where's the rest of this working? See that when I used that double angle formula? I used it backwards, really. I didn't need to figure out what sine of pi on 6 is. I knew what that was, or what cos of pi on 6 is. I knew what that was, but what I did is I used it to figure out the other bits. So you don't have to use them in any one direction because they're not actually rules for calculating. They are descriptions of how things are related. They just happen to be useful for calculating. But overall, they're just things about how they're related. And actually, the fundamental trig identity doesn't tell you how to calculate cos or sine. It just tells you something interesting about the way they're related to each other. So if you've ever been in the Maths Learning Centre and you hear me ask you, so how are cos and sine related? Which I can see at least one person smiling because he's had me ask him that before. That's asking you, what's the fundamental trig identity? But I don't think about it as the fundamental trig identity. I think of it as this is how cos and sine are related to each other. So it's useful to know that that's how a lot of mathematicians will think. And it's not the worst way of thinking to say, oh, what relationships do I have between these things? All right. Well, we have one more, possibly two more, but one more thing that's really important to talk about, which is we've missed a representation of these things. So we already have this thing with the unit circle, which is fabulous, and the thing with the triangles, which is another representation. This one only works for certain small angles, and this one works for all the angles. And we've got them represented as like abstract formulas that calculate one thing from another thing. You know, there's not really a formula, it just is what it is. And so we're thinking of them as functions in that sense. Function that, you know, you've got an input and it spits an output out. Damn it, that's the nature of these things. Darling West is one of the worst lecture theatres because the desks flip forwards and all your stuff goes under the seat of the person in front of you, especially if you're falling asleep. So that's my memories of first year physics. The other thing about the way functions work is that you're used to functions having graphs, or graphs if you like. So you're used to functions having graphs, and these functions have graphs too, and we need to know about how the graphs of these functions work. And suddenly, once we're interested in graphs, the sorts of things we can do to graphs will dictate this, will be interesting things that we can do to our sine and cos values as well. So we're now going to talk about graphs. Because it's all about connections, right? If these really are functions, then they really are, it is really possible to draw a graph to represent them. So, traditionally in this course you use t as the variable, don't you? You don't use x? Oh, that distresses me, but anyway. I don't know, it depends. your lecturer might have switched it up. Ray is the sort of person who would be a very logical and reasonable sort of person and would use x instead of t, but, you know. Oh, the world makes sense again. Okay, so you're used to seeing a function represented as a drawing on an x and y plane. Now, we've already got a drawing on an x and y plane, but this is not a picture of your function in the same way you normally see it. You have an angle measured around a circle, and the sine and cos are information about that point. Now, that's not the way you normally draw a function. You're used to seeing something a little more like this. You've got something that like goes, okay, I've got a table, right? These are my x's and these are my y's, and maybe the x is 0 and pi on 6 and pi on 4 and pi on 3 and pi on 2 and 2 pi on 3 and so on, right? And you've got these values, and the answers are for sine, let's just say that's sine x, 0, sine of pi on 6 is 1/2, 1 on root 2, root 3 on 2, 1, back to root 3 on 2. Okay, so that's one way of doing a function, right? Normally you make these equally spaced, but, you know, I'm just using the ones I happen to know the answer to. And then you could imagine you could have like an axis to hold your x values. And you draw heights or depths to represent the value of the function. And so here at 0, the height is 0. Here at pi on 6, the height is 1/2. Here at pi on 4, the height is 1 on root 2, which is about there. Here at pi on 3, the value is root 3 on 2, which is about there. Here at pi on 2, the value is about there. It actually sort of levels off a bit, and you get like something like that going on. And you can connect them up, and you could imagine calculating all of these points, and it starts to go back down again at 2 pi on 3. And you're used to seeing graphs of functions with tables like that, like this. And that's what we're going to do. And then what you do is you go, oh, all those heights, I'm going to interpret them as a y coordinate, and the coordinates of this point are pi on 2 and sine of pi on 2. Like that. Whoops. All right. And what that does, so your graph of your function originally technically didn't really have a y-axis. You just measured those lengths in every direction. But it became useful to have an axis to compare them to. And suddenly it also becomes a formula for telling whether a point is on a curve or not. I can pick a random point like pi on 2, 1.5, and I can go, is this on this graph? No, because the y-coordinate should be sine of the x-coordinate, and it's not. And so it's not on the graph after all. So now I've connected my function to this idea of an equation to tell you whether a point is on a curve or not. It's awesome. So what we need is to be able to draw what those graphs look like, and become very familiar with how those graphs look. And we've already got the beginning of it. Very bad sine graph. Not nearly as bad as my normal distributions over in statistics, but still pretty bad. Maybe one. There we go. Beautiful. I know I've known people who have a nice little template that they take to their exam to draw sine curves with, but didn't think it was ever worth the effort. Maybe I should have bought one. Okay, so that's what the sine graph looks like. What we're going to do is notice some things about this sine graph. When x is 0, it's 0. We knew that, because sine of 0 is 0. it starts going up first. All right, it starts going up first. Once it gets to pi on 2, it starts coming down again. And it goes up to 1, starts coming down again, and it keeps going down until it gets to -1 at 3 pi on 2. And then it comes back up again, and then does the whole thing again. So 3 pi on 2 being 1.5 pi. And back in the other direction, if you go downwards from here, it goes down first in the opposite direction. And in fact, we can start to see that odd and even thing, that odd thing, if you've got a plus value of the angle, and you go negative the same way, if it's down here, it'll be up there. And if it's up here, it'll be down there. So that's sine. Okay? Other useful things to notice is the entire graph is between +1 and -1. And in fact, if you shifted the whole graph over, it would be exactly the same if you've shifted it far enough. Cosine x is the same shape, but in a slightly different spot. Cos of 0 is 1, because on my unit circle, a 0 angle is there, and it's got coordinates 1, 0. So cos of 0 is 1, so it starts up here. And as this point moves around the unit circle, the x-coordinate gets smaller and smaller, and so it goes down first. And then once it gets all the way over here, the x-coordinate's negative, and then it starts going smaller again. And so it does that. And then it comes back down again. And it just does that wave forever. So the reason why sine and cos graphs are so useful is because a lot of the things that oscillate over time have graphs that look like this shape. And so it's a very useful formula to use to describe physical and financial systems that oscillate over time. And that's why in 1M they get you to learn all about it, because a whole lot of people doing 1M are doing physics as well, and in next semester in their physics courses they're going to need to know more about it. And so they put it in 1M. Also, cos and sine have this wonderful property about how their derivatives behave. If you are interested in things that have certain properties about their derivatives, then you'll have to use cos and sine. Tan, on the other hand, has its own shape again. All right, so let's think about what tan does. So my unit circle, tan of 0 is the slope of this line, right? Or possibly where that line meets the tangent. So it meets it at 0 here, so tan does that. As the angle moves around there, the tan value gets taller and taller, until when it's almost vertical, it's like miles away up there before it hits the tangent, and then when it's exactly vertical, it never meets the tangent, and there is no value of tan. So when we get to pi on 2, there is no tan. And so we draw a dotted line there to say there is no value of tan that lines up with that pi on 2. It's useful to know that here at pi on 4, the answer is 1. And if I go in the opposite direction, the same thing happens, but in the opposite order. Like that. There you go. And then this shape is copied forever in both directions. So once I get over to this side, when my angle's round here, it meets in the negative side of the tangent. And so here we are in the next zone up to pi, and it comes up here and then goes up again, and it's at 3 pi on 2 that there is no tan. And that's what tan looks like. So it's interesting to note that this graph is much less stretched out than this one. The sine only goes up to 1 here, just there. So sine goes up and down here, and the tan just shoots up. Okay. And there are other graphs. The reciprocal functions have their own graphs, and they are a whole different thing. So if you had y equals sec x, for example, which is the other really important one, it's 1 over cos. So what you can do is you can take your cos graph and you can go 1 over all of its answers. So at this position here, 1 divided by 1 is 1. And when we get down to here, when it's about a half, 1 divided by half is 2, and so it goes up to here. And 1 divided by a very small number is a very huge number. And here exactly at pi on 2, we're going to attempt to do 1 divided by 0, which doesn't exist. And so it's going to go like that. And then it'll happen again, only over the next zone it's negative. And then over here it'll be positive again. And so on. It's not particularly edifying, this graph, but anyway. It's just an idea of what happens when you do 1 over. All I would say is that see how this sec here has a zone between minus pi on 2 and pi on 2, and it's not defined at pi on 2? It's sort of the same thing that tan does. And it's one of the relationships between tan and sec, and we expect them to be very strongly related because of this original triangle that I drew. So, yeah. I'm not going to draw cosec. It's the same but shifted over. And cotan is 1 over tan, and it's actually just this but up the other way. So, actually, no, it's this shifted over pi on 2. Okay. So they're the fundamental shapes of the graphs. And it's very, very important for success in Maths 1M and Maths 1A and Maths 1B and Engineering Maths 2A and, you know, mathematical career in an engineering or mathematics or science degree to be able to draw a sine graph. If you see y equals sine x, you should be able to go bang, 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 done. Okay, it's the sort of thing that it's a good thing to be able to do. Just like being able to write your name is when you're in kindergarten, drawing a sine graph is the sort of thing you need to do at university. Okay. So I just had this vision of people, instead of writing their name on their exam, drawing a sine graph. Okay, so, right. So that's lovely, and it's wonderful. But there are other trig functions that you've already seen that being functions should have graphs. You've seen one already. We did one here, right? Sine 2x. It should be possible to draw sine 2x. And interestingly, it would be the same shape as this graph, which is much harder to imagine what it looks like. So it should be possible to draw sine 2x. It should be possible to draw sine x all squared, but we're not going to do that. Okay? So what we want to do is we want to be able to draw graphs that look a little different. And the reason why it's so important for science and engineering is that, you know, while things have nice wave-like shapes which look like sine and cos, they're totally not going to be exactly in the same spot as your traditional sine and cos graph, and you're going to need to be able to figure out formulas that go with them. And it's actually much more important in economics than it is in engineering, but you know, I'm not going to get into that. So you need to have ways of figuring out how graph functions line up with the values that they have. And this is the hardest bit, as some people who have talked about this today know. So, all right. Not hard, no, hard because you have to concentrate so hard the whole time in order to succeed at it. And I only do this once a year, like this process, when I'm teaching Maths 1M. And so I struggle, I don't do it often enough to be really good at it. I'm really good at doing matrix stuff that occurs in Maths 1A, because I do that twice a year, but Maths 1M not so much. So, all right, we want to figure out what graphs look like when the formula's a bit different. There are multiple ways of thinking about this. Hopefully you can pick one of them that I'm about to mention and run with that. So, right. So one of the ways of thinking about this goes with what happens when you take the value of your function and you do stuff to it after you've calculated it. So suppose you had sine x and you went, I'm going to, just because I felt like it, multiply that answer by 3 and add 5 to it. For no good reason than I felt like picking some numbers. What might that do to the graph? And one way of thinking about what it does to the graph is to think about what it does to the function values, instead of thinking about what it does to the graph. So I can imagine a table of values, right? I can imagine instead of having my points as a curve, is to go back to the way I represented them first. Okay, so there's my x-axis marked out in intervals of pi on 2. And originally, this was 1, and then these values in between were whatever they were. Okay. Oh, no, yes, that's right. Okay, so I can imagine it as made up of all these little lengths, either pointing up or down. And when I say this is y equals sine x at the moment, that's what these heights here are. And so what that means is that I've taken the value sine x and I've multiplied it by 3. So I've multiplied it by 3. And then I've added 5 to it, which has added an extra 5, so essentially, put 5 on the bottom or the top, if you like, so add an extra 5 on the top. Or alternatively, I've multiplied this by 3 and then added 5 to it, and since it's negative, that means I'm chopping a bit off of it. So I can imagine it like that. I can imagine that the value that's here has been stretched out and then moved up or down. So I can say that all these heights that I used to have are now, and depths are now 3 times what they were before. So this was 1 here. And now it's 3. Which doesn't look like 3, but it's bigger. Okay? So now this height is 3. So we have sine of 3 lots of sine x. And then what I did is I moved it by adding 5 to everything. So I had 3, and then I'm going to add 5. Add 5 to everything. Totally is not looking as good as I would like it to, but that's okay. Anyway, you add 5 to everything, and then you can connect up all those points, and it's whatever curve it is. That's the idea behind it. It's a pretty crappy drawing, I'm sorry. I should have brought the Cuisenaire rods. It would have been so awesome, but that's okay. Okay, So that's one way of thinking about it, thinking about the literal distances between the x-axis and the curve and stretching them out and moving them up and down. But some people just do it directly on the curve. They actually think about actually having their paper made of rubber and stretching it out by 3 and then shifting it over. And the axis is sitting in the same spot and the graph is moving on top of it. And so they think about this when they see this as sort of stretching out by 5, stretch times 3 and shift up by 5. And so what that means is your graph used to look like this, and it was 1 high, and then it became 3 high, and then everything shifted up by 5. So it became 3 high, and it was then this wide, and then I shifted it all up. And so this centre happened now at 5. There's 5. So I shifted the centre up by 5 and stretched it out by 3. Very bad graph, but that's the idea behind it. Okay, so that's thinking about what happens to your graph when you take the answer you've got and you do operations to it after you've calculated it. Sweet. But what if you did something to your x before you calculated the sine? What if you multiplied your x by 2 and then did sine? Now that's a whole different thing. That's a different thing entirely. I wonder if we can figure out a way of thinking about that. So that's saying that all right, let's do the inside. Let's do a 2x plus 1 here. Okay, so what this is doing is it's saying, first I'm going to get all my x's, I'm going to do something to them, and then I'm going to calculate sine. That's a bit trickier, right? So I've got a plan, it's not necessarily a good plan, but I'm going to run with it. These were my original x's before I did the 2x plus 1. I might do them in terms of pi. Oh, who cares? Can I do plus pi on 3 just so that I can do everything in terms of pi? Okay, so what I did is before I did the sine, I took every one of these numbers on the x-axis and I did times 2 and then plus pi on 3. So first I'll do the 2x. Okay, so here we go. This pi on 2 here, I times it by 2 and it ended up here. At pi. And this pi here, I multiplied it by 2 and it ended up here at 2 pi. And this 3 pi on 2, I multiplied it by 2 and it ended up over here at 3 pi. Okay, so everything's been stretched out, right? And just for completeness' sake, so I know what's going on, this minus pi on 2 got multiplied by 2 and it ended up over here at minus pi. Okay, so presumably this pi on 4 ended up here at pi on 2. and this pi on 6 ended up here at pi on 3, and so on. So everything got stretched out, okay? And then I'm going to add pi on 3. Oh, and the 0, I suppose, goes to the 0 as well, I guess, because when you times it by 2. So then I'm going to add pi on 3. And so this 0 is going to go up pi on 3. And this pi on 3's pi is going to go up to 4 pi on 3. And this 2 pi is going to go up to whatever that is. 2 and a third pi. 7 pi on 3. Okay, so everything's going to move up a bit. Okay, I'm doing well. And then I'm going to calculate sine on these answers. Because that's what I did. First, I times everything by 2, and then I added pi on 3, and then what I'm going to do is I'm going to calculate sine based on the answers that I have. Okay, so it's going to come out like this. Like that. That's how you calculate sine from an axis. So I'm basically ignoring where these x's came from and just calculating sine based on the numbers that I actually have. But the thing is, this is not the graph of my function. My function has these y values at those points. So this value just here, at pi on 3, which is about here, that y value there belongs to this x, because this is the original x that produced that y value. And so when I go back to my original, that's here. And this value here, 4 pi on 3, which is here, belongs originally to this pi on 2. And this value here, this green one, which is here, belongs originally to this pi. And so what I'm getting is a shrunk-in graph. So because I multiplied by 2 before I calculated it, and then took all these values of y and attached them to the original x's, my graph is further shrunk in than the way a sine graph normally goes. There you go. It's an illustration of something that says that if you multiply by 2, your graph is actually shrunk inwards. Everything's divided by 2 along the x-axis. And if you add pi on 3, that's actually the same as subtracting pi on 3. Everything moved over that way a little bit. Because my x's moved first, and then I took the values that they produced and put them back on the original. So I need to do this with Cuisenaire. It's going to be awesome. So that's a description of why, when I see this, what's actually happened is this graph back here, I have to do these operations in reverse and subtract pi on 3 from all the x's and then divide all the x's by 2. So let's actually see if I can make that actually happen. So this is y equals sine x. Like that. And this normally happens at 0 and pi and 2 pi there. So if I want to do the sine of x, I need to deal with the pi on 3 first. I need to work my way outwards. So I need to subtract pi on 3 from all of these x values. So this 0 here becomes minus pi on 3. And this pi becomes 2 pi on 3. And this 2 pi becomes 2 pi minus pi on 3, which would be 1 and 2/3 pi, which would be 5 pi on 3. And this becomes, I guess what we're going to do is we're going to add a pi, aren't we? 8 pi on 3. Okay, so everything gets a pi on 3 subtracted. So the first thing I did is subtract pi on 3, because I'm working my way in. And then I'm going to have to divide by this 2 to get back to the x. So I'm going to divide everything by 2. And so these are going to become pi on 6. Pi on 6s. And that's what my graph looks like. So I just did it by changing what was on the x-axis rather than actually shrinking the graph. Ta-da! There you go. And I think that's much more productive, Adrian, than what we did earlier today. Okay. And if you have to do something both on the inside and on the outside, well, I recommend doing the inside and then the outside. It doesn't really matter. They can be done independently of each other. But remember, the inside, you have to do the opposite of those things in the opposite order to the x-axis. On the outside, you do them in that order to the y-axis. And it's just because what happens before the function and what happens after the function behave differently, really. Okay, I guess the last trick is trying to guess what a particular graph actually, what its formula actually is. And that's the last thing that you might want to do in this setting. So we're not guessing, we're being sure. So finding what the formula. So we're going to find some formulas for graphs. Okay, so we just have to do this process backwards. And part of it was already backwards, but, you know, deal with that. So I guess the best to do an example, I suppose. That's supposed to go down to the bottom there. All right, that's my graph. It's sent, yeah. All right, tell me what you notice about this graph. Sorry? What do you mean by out of phase? All right. Where would you expect it to be? So you'd expect, if this was a cos, you'd expect that peak to be there. Okay, cool. I guess if it was sine, you'd expect the thing that's over here to be there. Okay, cool. So it looks like cos seems like the easiest thing to deal with because I know where the peak is. Okay, cool. What else do we notice? It's blown up in size. How can you tell that? Oh, okay, so are you talking about this distance? Yeah. So from there to there is 3 and from there to there is 3. And normally it's what, 1? Okay, cool. Anything else? You're saying it's shifted up by 3. Is that, what's causing that? Which of these 3 lines? because that normally happens on the x-axis and it's happening at the line y equals 3. Okay, cool. Anything else to notice? There's one number we haven't mentioned yet. We've mentioned this distance and we've mentioned that number. We haven't talked about this number. How wide is this distance normally in a cos graph? It's normally pi, is it? Just a second, we've got one here. Yes, in a cos graph, that loop from top to bottom is normally pi wide. And how wide is it here? Oh, that is pi. Nice. Good. Okay. All right. So let's just think about what that means for my x-axis. My x-axis has not been stretched out. This distance all the way from the top to the bottom is usually pi, and it still is. So my x-axis, nothing's been done in terms of the stretching. Are you okay? Yeah, because to go from top to centre is usually pi on 2. Top to middle is pi on 2, and middle to the next is pi. And alternatively, one full cycle is 2 pi, and I've only gone half a cycle. All right? I'll let you process that. Okay, so in terms of my x-axis, I haven't done any stretching. No x stretching done or shrinking done at all. Okay? My x shifting looks like it's shifted forward pi on 4. The graph has moved there. And what normally causes a shift forward of pi on 4 is a subtraction of pi on 4 to the x. So what's that going to be is like an x minus pi on 4, because we know it goes backwards on the inside. The y stretched was 3, it's times 3, and my y shift was up 3. Okay? Beautiful. So it looks like we're going to have, it was a cos, wasn't it? Because it's been moved over from the cos. We've stretched it by 3, and we've moved it by 3. That's dealing with the y. With the x, we didn't do anything with the stretching, and we moved it by pi on 4. Yep. What? No, I think it's the same width it was before.
So the distance between pi on 4 to 3 pi on 4 is 1/2 pi?
Oh, it is totally yes. Beautiful. I was wondering what you were talking about. You were talking about this, not the other one. Right. Good point. We should totally have calculated that ourselves. 3 pi on 4 minus pi on 4 is 2 pi on 4, which is pi on 2. Yes! And I now remember doing that deliberately when I did it. So, okay. So my x stretch is not none. Let's just go back to that. We've actually halved it, right? It looks like it's times a half. But what that means is that we've actually done sort of 2x. Now, the question is, what order did we do these in? Did we do the 2x before the x minus pi on 4 or after? What do you reckon? And some votes. When did we do the shifting by pi on 4? Did we do it before we stretched out the x-axis, or shrunk it in our case, or did we do it after? After. How can you tell? Well, I can tell because if I had done it after, this would have been a pi on 8. I made, in my imagination, I changed the width and then I moved it over. I just need to be careful about that because what that means is that whenever you do one of these things, remember we're doing them in the reverse order. So we did this first and then this, like in terms of the moving of our graph. In terms of the maths we calculate, we have to calculate them in the reverse order. So we have to do x minus pi on 4, and then the 2. And we can always be certain that we've done it the correct way around by checking to see if this formula matches our graph. This should produce the answer 6 when x is pi on 4, according to this graph. Three cos 2 lots of pi on 4 minus pi on 4 plus 3. Now that's 0, and cos of 0 is definitely 1, and produces the answer 6. So it is matching correctly at that point. If I had done 2x minus pi on 4, it would not have come out to the answer 6. It would have come out to the answer 3 on root 2 plus 3. So just pointing out to that, if I had done that, then when x was equal to pi on 4, we would have got y equals 3 cos 2 times pi on 4 minus pi on 4 plus 3, which would have come out to 3 cos of pi on 4 plus 3, which would have been 3 on root 2 plus 3, which is totally not 6. So we definitely did the right one. So my advice to you is that if you would like to use this number here, the shift, as it is written, then you need to do this. You need to put it inside the brackets and then do the multiplier. Because it doesn't work otherwise. Yeah. Everything has to be in reverse. There you go. I think that's everything that's in trig, other than derivatives. Damn it. The recording's going to stop in 2 minutes. I don't know how to make it go longer. Damn it. Okay. Okay. All right. Well, the only other thing is derivatives. And in essence, your normal rules for derivatives, which is a whole other seminar, apply in terms of the product rule and the chain rule and all of those things. And you just need to know what the rules are for how to differentiate these things. If y is equal to cos x, then dy and dx is minus sine x. And if y is equal to sine x, then dy on dx is cos x. And if y is equal to tan x, then dy on dx is sec x squared. Which is good. That makes sense. tan has always got positive slope if you go and look at its graph, and so the squared makes sense because it should be positive all the time. A lot of people have trouble remembering which one has the minus. And you can always check it from the graph. So in y is sine x, you know that when x is 0, the slope here is positive, properly positive. So here, so if it was minus cos x, then cos of 0 is 1, and the answer would be negative 1, and it's pointing in the wrong direction. So you know it can't be the minus here, because it doesn't match the graph. There you go. I have a very, very bad way of remembering, which has nothing to do with the relationship between the function and its graph, and it's to do with alphabetical order. So if you go, so when you go from cos to sine, so we're differentiating. Differentiation is down and integration is up. That's how I always think about it. Because with powers, right, if you differentiate x squared, it goes down to x. If you differentiate x to 5, it goes down to x to the 4. So differentiation is down, right? So if I wanted to go down from c to s, I can't, right? I have to go up from c to s. And so I'm going the wrong direction, so it's a minus. It's so bad. So I go down from s to c, correct direction, so it's a plus. That is the worst thing ever, but it works for me. But I have a big alphabetical order thing with the cos and the sine. Your fundamental trig identity, personally, I have to write it cos squared and then sine squared. They have to be in alphabetical order. That's just one of my things. And it's not just one of my things, because when I do hyperbolic trig, they have to be in that order or the formula's wrong. So, yeah. Yay. All right, well, thanks, guys. I'll probably do another one of these next week. I haven't decided exactly what day. It's likely to be Tuesday.